Thank you, Raphael, and thanks for the invitation. It's a pleasure to be here, and I'm very excited to be joining you all in the fall. So today I'll be talking about bootstrapping quantum extremal surfaces. This is based on a paper I wrote last summer with Alex Berlin, as well as some ongoing work with Alex, because it's a larger program, which I'll describe. So to start us off, as I'm sure many of you are familiar with, there's this formula for the entanglement entropy in a CFT for some region A. And the proposal of Engelhardt and Wall is that this is given by extremizing the generalized entropy. So we consider the area operator in the state psi for some codimension 2 surface gamma plus the bulk entanglement entropy of quantum fields bounded by this surface gamma and the boundary. So let me draw the picture. Here's a slice of ADS3. Here's some boundary region A. And here's some surface gamma. And this is my homology surface sigma bounded by gamma and A. And the prescription is that to compute this CFT entanglement entropy, I should extremize this generalized entropy and take the minimal surface. So that's the prescription. And today, the goal is going to be to try to understand this prescription. So this object here is the generalized entropy for this state psi. OK, good. And this has been a central player in our understanding of the connection between quantum gravity and quantum information, although the connection is obviously much more general. And so we want to unpack this formula. So this is expected to give the entanglement entropy order by order in 1 over c. And so today we're going to look at this formula perturbatively in expansion in large C or large N and try to match terms between the two sides. So one major motivation for this is that the recent developments in the page curve has shown us that in order to reproduce the page curve from this formula, you only seem to need semi-classical gravity. You don't seem to need all the UV physics, all the strings and branes and so forth. And so the question is, how much information in the CFT do you really need in order to understand the right-hand side, in order to compute the right-hand side? And so today I won't consider black holes. That's too complicated. Instead, I'll ask a simpler question, which is just perturbations of vacuum ADS, and ask, can we construct a dictionary between these two sides and understand how the physics of these quantum extremal surfaces is encoded in CFT data, say the OPE data. So the goals are to construct a dictionary between CFT OPE data and the data of these quantum extremal surfaces. And the second is just to explicitly check this formula, so the QES formula. So to our knowledge, there are actually no explicit checks of this formula. I mean, it's been applied in beautiful ways in computing the page curve. But to our knowledge, no one's actually computed both sides and checked that they agree. And so a second goal is just to actually check this formula and make sure that it makes sense and sort of understand the rules. Because once you start to back react on the geometry order by order, there's lots of subtleties. And I'll explain them as we go. And understanding these subtleties is important for understanding this formula.
You asked for high level of generality in my way of that statement? Because, I mean, for example, in the original HEP paper, right, they checked that in that case, of course, you just look at the area, you don't include the rest, and you check that it matches the entanglement entropy of the interval in a CFT or in a 1 + 1 CFT. So when you say that nobody's actually checked this formula, what sort of arena do you have in mind?
When the bulk entanglement entropy term becomes important, you have to actually extremize this combination. That I've never seen computed explicitly. So extremizing this generalized entropy and matching it to a CFT answer. So people have certainly computed this generalized entropy, say in JT gravity, in these evaporating black hole models, or even in higher dimensions for this double holography. But I haven't actually seen anyone match it to the CFT answer.
So in any situation where the area of the quantum extremal surface is affected by the presence of matter entropy.
Exactly. When you're no longer just considering the classical extremal surface, but really the quantum extremal surface. OK, I should say that there is a proposed argument for this by Lefkowitz and Dong, where they argued for this using a Lefkowitz-Maldacena type trick. But there's lots of subtleties in that proof that they give. And so unpacking this formula and understanding it more carefully is, I think, important. OK, so maybe I'll just write down the dictionary quickly so you all can see where we're headed. And then the rest of the talk will be deriving this dictionary. So so at order C to the 0, I'm going to be working in the context of ADS3-CFT2 in this talk, so I'm going to use C instead of N. C is the central charge of the conformal field theory. So at order C to the 0, there are two contributions that you get to this. One is the contribution of the identity operator in the S channel in the OPE, as I'll explain. And another is the contribution of double trace operators. And in the bulk, you get two contributions at order G Newton to the 0. You get a contribution coming from the back reaction of a scalar field psi on the metric. And you get a contribution from the Bulkentanglement entropy. Notice that there's no contribution from a variation of the metric because of extremality. Classical extremality says that there's no gamma 1 G0 term here in this expansion. And this was explicitly computed by Belin, Iqbal, and Makande. And they computed these two sides and matched them and constructed this part of the dictionary. So this is what they call FLM order, Faulkner, Lefkowitz, Maldacena, where there's no extremization here. So at first order in G Newton, there's no extremization. You just have the area of the classical extremal surface plus bulk entanglement entropy across the classical extremal surface. So the goal today is going to be go to next order, where quantum extremality becomes important. This is the area of the classical extremal surface for the back-reacted metric. So G1 is the back-reacted metric.
But it is still back-reacted, despite the fact the location is the same?
That's right, yeah. So the location is the same, but there's a correction to the metric from the back reaction to the scalar field.
It's just still determined by G0.
Exactly, because of classical extremality, there's no first-order variation in the surface, position of the surface. These are double trace operators.
How should I think about how you're computing the entropy here?
Yeah, I'll explain this in more detail, but the way we're going to compute this entanglement entropy is using Renyi entropy. And there we'll end up with a 2 endpoint function of some primary operator. And when you take the OPE limit between the two operators, O and O, there's different contributions to this OPE. And the leading order is the identity, and then there's a subleading order from the OO double trace block.
So we're in a 1 + 1 dimensional CFT?
That's right.
And why are we taking the OPE of the 2 endpoints?
I'll explain that, but the OPE comes from taking a small interval limit in the CFT. So when you take the small interval limit, these operators will become close. And this will be the contribution to the OPE. So
only analyzing things in some kind of small, what does this mean to take
But when you take the small interval limit, you'll see that you get an OPE limit for these operators O. So I'll explain that. I'll come back to that later. Yeah. Here I just wanted to give a general picture, but I will definitely describe all of this in more detail. And then there are various contributions in the CFT. So one comes from an anomalous dimension of this operator O, which I'll explain how to compute. And then another comes from the stress tensor contribution in the OPE. And then these double trace operators receive corrections to their anomalous dimensions and corrections to their OPE coefficients. Okay, and so today I will show you that this matches to the area term. And then these terms presumably come from the Bulkentanglement entropy, but this is work in progress, so we don't yet know how to match these to the bulk. We know how to compute these in the CFT, but we don't know what they correspond to yet in the bulk. But today I'll explain this term, and this term indicates that the area term contributes solely to the Virasoro identity block in the CFT. So this is the contribution in the CFT of the Virasoro identity block. Okay, so that's just painting a general picture, and I'm going to explain all of this in much more detail and how we get this dictionary. Now, one comment I should make is that, in general, the individual terms in the generalized entropy are not well defined. So this is an old problem that's been known, that both terms are divergent. Both the area term and the bulk entanglement term are divergent, and you should only consider the combination. And the divergence from the entanglement entropy renormalizes G Newton, and that equation with renormalized G Newton is a finite quantity, and that's the only thing you should really consider. So then you would say, okay, this whole program doesn't make any sense. You can't distinguish different contributions in the bulk, say bulk entanglement and area pieces. And what turns out to happen is that we're going to consider the vacuum subtracted entanglement entropy. And that vacuum subtracted entanglement entropy will actually be finite. And so it makes sense to actually identify these different contributions with the CFT. Okay. So you can still subtract the area of the vacuum surface and the vacuum metric. The classical extremal surface with the vacuum metric, you can compute that area and subtract it. And similarly for the entanglement entropy at leading order.
So you work with G0.
Yes. Yes.
Why doesn't that sort of become wrong in the sense that you're worrying about higher order corrections?
I don't think the vacuum piece here gets any correction at higher orders. Like there's no quantum extremal surface if you're just in the vacuum state. The quantum extremal surface is the classical extremal surface. I think you need to consider an excited state in order to get these contributions that come from the quantum extremal surface.
Sure, but the excited state does appear in the calculation of the vacuum subtracted entropy.
Yes.
And you're looking at its entropy in the unperturbed vacuum. I find that confusing because you're going to higher and higher orders here. This is some schematic expansion. So as soon as you include like corrections to the metric, even at first order, then the region to which you're trying to reduce doesn't have. Let's see. What you need is the same universal divergences to appear.
Yeah, and that's what happens. So what I compute is this And these seem to have the same universal divergences. So this quantity seems to be finite, at least in terms of our calculation.
What does this quantity mean? Can you just say what the quantity means for the vacuum?
This is, you extremize the generalized entropy for the vacuum state.
Sorry, I thought that what you're trying to do here is define the entropy by itself. In other words, I mean, if you're working with the generalized entropy, then we don't have any problem making it well defined anyway. At least we think we don't.
Right.
What you were referring to is a difficulty of just defining the entropy of the matter by itself, some kind of renormalized entropy of the matter.
Yeah, so that thing you need to renormalize because it's divergent. And I don't think it makes sense to try to attribute necessarily that to the bulk, between the bulk and the boundary. It's not clear, at least, how to do it.
Can you say again what you're using the vacuum subtracted entropy for?
Just to subtract off divergences. So here it subtracts off the leading divergence in the area term, and it subtracts off the divergence in the bulk entanglement term.
So
And similarly,
that has an EE as a subscript is a vacuum subtracted entropy.
it will be, yeah. So right now I've just written this, but yeah, eventually this will be delta. That's right. So maybe I can come back to this after, if it's still confusing. Okay, so let me give an outline of where I'm headed. So, okay. So first I will tell you about the CFT entanglement entropy. Then I'll tell you about the generalized entropy. And then I'll finish with some conclusions and open questions. Okay, so let's get started. Okay, so I'm going to consider some state O, which is some operator acting at the origin on the plane, on the vacuum in the CFT. And this operator is going to have some order 1 dimension, so it's some light operator. And my boundary region is just some angular interval of size theta on the cylinder. And so the density matrix, I'm going to use psi and O interchangeably because psi will be the bulk state. So here's my reduced density matrix on A in the excited state. And we're going to use the replica trick to compute the von Neumann entropy. So we're going to compute delta S of A and this will be the limit as n goes to 1 of the vacuum subtracted Renyi entropy. Okay, so to compute this vacuum subtracted Renyi entropy, let me write the formula, and then I'll explain how it's computed. Okay, so what you do is you take this density operator and you take n copies of it, and it's n copies of the cylinder glued across A. You map that to the plane, and then you uniformize the plane by taking the nth root of that map. And what you end up with is this 2 endpoint function of the operator O. And now these operators O are arranged on the unit circle in the plane, and they're arranged like this. So this distance here is theta, and here let me draw n equals 4. So there's 8 operators, and they'll be arranged like this around the unit circle. And so this is O of zk tilde, and this is O of zk. So to compute this, this vacuum subtracted Renyi entropy, we just need to compute this 2 endpoint function of O. And so this 2-point function will receive different contributions. And in particular, in the small theta limit, this becomes the OPE limit, where these two O's are becoming close. So at order C to the 0, you just get generalized free fields. And this receives 2 contributions. So there's the identity operator in the OPE, and there's this double trace operator. This is at leading order. That's right. Yeah, so the vacuum subtraction, usually when you do uniformization, you get some infinite factor coming from an infinite conformal factor. So usually we instead use twist operators. But this vacuum subtraction removes that infinite conformal factor, what you get from uniformization. And so you get this nice finite quantity in the CFT.
I'm sure I'm just thinking of this the wrong way, but naively I would have been a little worried about taking theta to 0 because, well, I mean, if I actually did worry about the vacuum entropy itself, right, that entropy would be like C over 6 times some log of the width of the interval in units of some cutoff. And it wouldn't make sense to take the width of the interval to 0 because it would always become smaller than the cutoff when you do that. But is that an issue that sort of drops out when you subtract the vacuum and you get to...
Theta should be bigger than cutoff.
Yeah, I think theta still needs to be bigger than the cutoff, but it's small. And I think you just take some order of limits, where you take epsilon to 0 and then theta to 0.
Right. I guess the point is that you can take epsilon to be much smaller, and that gives you a huge contribution that drops out.
Right. Right.
So
Yeah.
you have a CFT vacuum state. You operate you add operator O at some point at 0.
Yeah.
And then you're taking A to be 0 to theta. Is that what you're doing?
Yeah, sorry. This is 0 in the plane, so it's really minus infinity on the cylinder.
Okay.
And then the interval is, yeah.
Okay.
Yeah, exactly. So the picture is...
I kind of expected.
Okay.
I suspected that you know this.
Yeah, here's the operator O, and then here's theta. Here's A.
And maybe I'm kind of skipping ahead. And this vacuum subtract the short distance divergence in CFT, meaning that you have divergence from both point of view. It's a divergence coming from the endpoint or boundary and going to length maybe. But then still, that's not like individual divergence of A at S bulk. Adding that is finite, right?
Yeah. If you
resolving this, yeah. Or this vacuum subtraction at the CFT level has nothing to do with the separation between A and S bulk.
Yeah, that's right.
So will you explain that?
I will explain that, yeah. Yeah.
So that was the issue you're trying to talk about, right?
Yeah. Yeah, so I'll come back to that when I talk about the generalized entropy. Okay. And then at order C to the 1, there are various contributions. So there's one that just comes from this correction to the dimension of O, which I'll talk about later. There's another one which comes from the T exchange. So here I'm assuming that I have some low energy effective field theory in the bulk, where all I have is the operator O and double traces of O and gravity. And all the stringy modes are suppressed by some delta gap, 1 over delta gap. So here I'm assuming that at leading order in delta gap, I just have T exchange and the double traces in the CFT. no other single trace contribute. So then there's these anomalous dimensions of the double trace. And the corrections to their OPE coefficients. And these things can actually be computed. So they were computed, one place they were computed is in this paper by Collier, Gobay, Maxfield, and Perlmutter, and using large C bootstrap techniques, and you can actually explicitly compute all of these contributions to this OPE. So then we plug it into this formula, and we take the n goes to 1 limit, and we can actually compute these. So here's what you get. This is the term from the correction to the dimension of O. This is the contribution from the stress tensor. Okay, and then these contributions are a little more complicated, coming from the double traces. So I'm not going to tell you explicitly what these functions are. You can find them in the paper. But there's some function of h here, some complicated ratio of gamma functions. Okay, and then there's the final contribution. Okay, so that's the full contribution to the CFT. There's these 4 pieces, and we computed them explicitly in the paper. Oh, this is 2 delta H. So that's the delta H here coming from the correction to the dimension of O. Okay, so that's the end of the CFT story. I should pause here for questions to see if people have questions about the CFT calculation. Okay, good. If not, let me talk about the bulk, because that's the more interesting and complicated part. Okay. So let's talk about the generalized entropy. Okay, so this operator O that constructed the state O by state operator correspondence, this corresponds in the bulk. There's a corresponding scalar field phi dual to O, and the corresponding state is just the creation operator acting on the ADS vacuum. So that's the dual state. And so we're going to be considering expectation values of the area operator and the Bulkentanglement entropy for this state. And I'm going to call this state psi. Okay, good. So I already told you about this leading order piece. Let me write it again.
Are you saying you're restricting to operators in
Yeah, that's what this corresponds to, this operator, this primary operator O.
Because O is a primary, so it's just I.
Exactly.
Oh, sorry.
Yeah. So the A and L would be descendants of O. Yeah. Okay, so here we have 1/4 psi expectation value of the area operator So psi naught here means that I've quantized the scalar field on vacuum ADS. So that's what psi naught is.
Maybe one last, but CFT, if you excite my primary operator, at short distance, it looks like vacuum.
But then there's corrections to the vacuum.
But in the limit that theta goes to 0.
Yeah, and the limit that theta goes to 0, yeah, I think this will all drop out. There's no order theta to the 0 piece. So everything is proportional to theta.
So that's why I'm confused with the delta S1 or delta S3 log of 0.
Oh, these terms, let's see.
That's the reason I asked.
Yeah, so I think in the vacuum you won't even have this because there'll be no gamma 0, 0 or delta H.
Yeah. But with the correction you have this, which is not going to 0, and the limit that the region is small.
Let's see, did I miss oh, actually, you know what? I think I have a typo. There should be a sine theta term here. That's what's going on. I wrote something wrong here. Thank you. Yeah, there should be a sine to the 8H here. Yeah, thank you. Okay.
You were worried about the sign being inside the log.
No, but it's not. I mean, with the sign.
Now there's another one outside.
Yeah. Okay. Okay, and then there's the bulk entanglement term. Oops, this should be G0. Okay, good. So this is just the bulk entanglement across the classical extremal surface in vacuum ADS. And as I said, this was computed in the paper by Berlin and friends, and it matches the CFT answer to this order. Okay, so now let's talk about next order. So these are all the terms that don't get extremized because they depend on the classical extremal surface. Yeah, 0. Okay, and then there's the piece that actually comes from extremizing. So this is the quantum extremal surface piece. Okay, now let me explain all these different terms.
All going there, even at order G is 0.
Uh-huh.
And But subtracted. But earlier you said on the table that this A piece corresponds to some piece, and SEP piece some piece. How you can do that? Because those are just cutoff dependent, both cutoff dependent.
Yeah, so the way you match them is that, so this term has some contribution that goes like theta squared plus theta to the fourth plus dot, dot, dot. And this has some contribution that goes like theta to the 8h. And so you just match them by their monodromy in the complex theta plane. Like these have different, you can expand these differently because they have different monodromy in the theta plane. And so clearly they're distinct contributions, and then you just match the theta squared terms to the identity and the theta to the 8h terms to the double trace in the CFT. Yeah. Exactly. That's the key to matching this dictionary between the two sides. Because h is some general number. It doesn't have to be integer or anything. Okay, so.
Still for arbitrary value of theta, the divergence piece cancel out.
That's right.
So how because if you think about the theta series expansion in theta, if order is different, diverging and diverging.
The leading order divergence gets canceled in both cases. In the entanglement entropy, it gets canceled against the vacuum entanglement entropy, and in the area, it gets canceled against the vacuum ADS area. They just, each of these terms separately cancels. You compute each of these as vacuum subtractions, and they're finite.
So vacuum subtraction won't cancel these divergence, right? Vacuum subtraction in CFT is subtracting short distance divergence in CFT. So you're just only taking care of this infinite length towards infrared from Bulk point of view. What I'm talking about is the power divergence of A and the power divergence of S.
The bulk UV divergence is that. The bulk UV divergence. The bulk UV divergence, like the divergence across the classical extremal surface. That divergence?
Yeah, entanglement entropy, bulk entanglement entropy.
Yeah, so in here when you compute the entanglement entropy, you can subtract off that UV divergence. It comes from the vacuum. Because it's a short distance divergence, so it comes from the vacuum entanglement, and it gets subtracted. So let me say.
These are both vacuum subtracted terms, right? Both the area and the entropy in your first line
Yeah.
are already vacuum subtracted.
This is delta S. This is intrinsically vacuum subtracted because it's G1, it's not G0. So maybe I should put a delta here, but I think here I don't need a delta because it's G1. So what I subtracted off is gamma A0, G0 here, right?
You're basically matching a change in the entropy when you excite the vacuum in the CFT to a change in the entropy in the bulk.
Yes.
You're never really comparing,
Right.
In your second line, did you put 0, 1, 1 there in the third term of the second line?
This third term, this term?
No, 1, 9.
Oh, this term? So let me explain actually each of these terms. So this term we're going to compute by backreacting a second time. So we're going to backreact the scalar field twice on the metric, and that'll be this contribution. This contribution is the change in the bulk entanglement entropy due to a change in the metric. This term is a change in the bulk entanglement entropy. This term is kind of actually more subtle. So it comes from this phi 1 piece, and it's due to the fact that at first order, two particle states in the bulk now pick up an anomalous dimension due to gravitational interaction. So you now have a binding energy of two particles in the bulk, and that binding energy corresponds to a shift in the entanglement entropy. So that's this term. And that corresponds to the anomalous dimension in the CFT. It's a corresponding anomalous dimension. The double trace anomalous dimension and this two particle binding energy due to gravity is the same contribution. So that's that. And then this is the quantum extremal surface term. So I said that this term is 0 by classical extremality, but this is really like shape variation of the surface squared. So that term is not 0 by classical extremality. And then there's shape variation and metric variation of the surface, some contribution to the area from that. And then this is the bulk entanglement entropy due to the shape variation. Yeah.
It's just a change, yeah. Because all of the divergence I'm talking is a vacuum physics. You already subtracted.
Right.
So maybe now I can come back to my question from the beginning, because I'm so confused how you compute a vacuum subtracted For example, the area is different, right? So the area divergence, if it was before, it was some area over epsilon squared, and now it's some other area over epsilon squared. How can those two things cancel?
So at first order, so like this term,
Here I'm not worried.
here you're not worried. Here you're worried about this, such a term like this.
Well, I was worried mostly about the vacuum subtracted entanglement entropy, SEE.
Yeah.
Because, yeah, it's not clear to me how you match there doesn't seem to be a universal sort of matching divergence anymore once you have different matches.
Yeah, so we seem to be finding indication that this thing is actually finite. So the way you compute this thing, which I'll get to later, is by this Rosenhaus-Smolkin formula. So it's a two-point function of the stress tensor and the modular Hamiltonian, integrated over all of Euclidean ADS. And that thing, at least from our calculation, seems to be finite. This TK two-point function in ADS3 seems to be finite. But we need to do more checks. I mean, this is the part that I'm not going to talk about today because we haven't finished calculating all of it. So I can explain more offline why that term seems to be finite, but it's kind of a complicated reason. I don't have a deeper explanation for why it should be finite. Yeah.
That means, so you were worried about the interaction between two particles in the bulk?
Right.
How did you get two particles given that you acted only once?
When you compute powers of this thing, when you compute by Renyi entropy, you end up getting two particle states. Because there's a contribution. So I should say the way you actually compute this term is by going to Rindler coordinates for the entanglement wedge, and then considering this as a perturbation on the thermal state in Rindler, and then computing it via replica trick. And when you compute the Renyi entropies, you get multiple of these A's. Exactly. Yeah, so this term is basically coming from computing this term, but with corrections due to gravity.
It would be nice to have a more sort of, I don't want to say intuitive or principled understanding of why. I mean, when you do a calculation and you get everything worked out and it's finite, that's great. There's probably some reason for it, but I don't understand how you're making sense of these vacuum subtracted entropes. It seems like you're kind of doing the right thing, but it would be nice to distill from that some prescription for how to define vacuum subtracted entropes in some perturbative expansion where the metric is actually not identical in the excited state and the vacuum state.
Yeah, I agree. And I should also say that in general, you can have state-dependent divergences. Like there's this paper of Wall and Marolf where they showed that if you have two scalar fields in the bulk, you can get these state-dependent divergences. And I think in that setup, you probably won't get these finite things. So we're considering a very simple class of states where we seem to be getting finite answers. But whether or not it's true more generally, I have no idea. OK, so I don't know how I'm doing for time, but.
Can you do like at least for 20 minutes?
20 minutes. OK, great. So maybe I can tell you how to compute some of these things. Whoop. Oh, there we go. OK. Oh. OK, good. OK, so you can compute this.
I'm sorry to interrupt you.
No, it's OK.
These are in some sense particles that are created at the center of ADS, right?
Yeah.
And then you're making theta small. So maybe you're helped by the fact that the RT surface is in some sense in an asymptotic region where you've hardly done anything.
Right. Yeah, we're very close to the boundary.
If you kept theta at pi or whatever, then would you still know how to define the vacuum subtracted entropy at this order?
I'm not sure. Yeah. Yeah, we are very close to the boundary. I'm not sure what happens non-perturbatively in theta.
Sorry, well, if you vacuum subtract, everything is finite, right? Because you think about area.
Yeah.
Which
Yeah.
And that portion is common in the perturbed system
Yeah.
and an original system, because number of fields is the same and everything is the same, so divergence is common. So if you subtract it, the area piece is finite, right? That's what you're doing. And the generalized entropy is always finite because divergence cancels.
Yeah.
So that means the generalized entropy piece is also finite. So once you subtract it, the backwards,
Yeah.
everything finite, right?
I think so. I think so.
I'm sorry, I don't agree at all. I mean, it doesn't make, vacuum subtraction doesn't make sense when you talk about solutions with different metrics. You cannot subtract, because the divergent pieces have to cancel. So if you're subtracting the entanglement entropy in some region from one in a region with a different shape, there's no reason for the divergences to cancel. And I think what might explain this happening here anyway is the fact that you have your big ABS, but you're making this interval very small, and so your RT surface is out near the boundary where your metric perturbation may be small enough that the divergence is still canceling. I don't know exactly how to quantify that, but it seems to be that's what comes out of the calculations. So.
But in general, it just doesn't work then even in that extent, because the area over G Newton piece of the divergence, and if you change the area,
Yeah, that's what I'm
right,
saying.
and then it's divergence, then even if you go into there or something, it's just always, as long as the area changes, it's divergence.
Well, this might be some order of limits issue. So they always think that theta goes to zero limit in the end.
In fact, that was my kind of original question also. Area piece and the next box, it's each divergence. How to separate? Usually you get the bulk. So I think the background subtraction works out. Then
What's interesting is that it seems to be that you're just at that sweet spot where it's not trivial but it is well defined. I don't know why that's happening, but I think it must have something to do with taking theta to zero.
Yeah. Yeah. Yeah.
If you did like a Beckerman-Graham expansion or something like that, it would still be at the same order. So I mean, that's essentially saying it's close to the boundary.
I mean, in general, you would expect that if the two areas are different, you subtract the divergences, you just get a divergence, right? And here, somehow, just that gets multiplied by something small to just give you a finite value, not zero, just a finite.
Yeah.
It's amazing, but I don't know why.
yeah, not that small would help because theta is left as a theta. So
Yeah.
coefficient of theta is finite. The grade is.
Yeah.
Yeah.
So still missing.
Yeah. Okay. So so this we backreact twice on the metric, the scalar field, and you can compute this corresponding contribution. And amazingly, you can actually do it analytically. Okay, the expressions are in our paper. I won't write down the expression for the metric, this G2. It's some very complicated thing, but it can be done analytically. And then you can compute the area, and you get some explicit formula at small theta. I'm just going to write this here to show to you that the match between the bulk and the boundary is highly non-trivial. Okay, and then there are some terms which depend on theta to the 4h and theta to the 8h, which we compute in our paper, but I won't write for you here because they're complicated. If you're interested, you can go look at the paper. Okay, and now I need to come back to this delta h, which I think I've erased. It's up there at the top. Where did this delta h come from? So what you do is you take the second order backreacted metric and you compute the ADM energy. So the ADM energy of the space-time, which we computed. So the leading order piece is just the Casimir energy on the cylinder. And then the first order backreacted metric gives an energy to h, which is the energy of the operator O. And then there's this 1/c correction to the ADM energy. So this operator O is not protected by supersymmetry or anything. So in general, it can have an anomalous dimension, and you can just compute it by the ADM energy of the corresponding spacetime. So this is delta H. Whoops. This here is delta H. OK, now let me talk about the quantum extremal part, and then I'll be done. So we need to extremize these three terms. So how do we do this? So we can go to Rindler coordinates. Yeah, exactly. So go to Rindler coordinates adapted to the classical extremal surface. So, okay, this is the metric in ADS3 for Rindler. And one of the really nice things about going to these coordinates is that the classical extremal surface is just at rho equals 0. So now the full quantum extremal surface to first order is just some function rho 1 of x, which we need to find. OK, so we have these two terms, the area term and the bulk entanglement term. This bulk entanglement term this is the Rosenhaus-Smolkin formula for shape variation of entanglement entropy. So it's an integral over Euclidean ADS3 So you can think of this delta G as a diffeomorphism that moves you from gamma 0 to gamma 1. And it's this two-point function of the stress tensor and the modular Hamiltonian for the state psi, evaluated in the state psi. And after integration by parts, it can be written in this nice form, where it's just an integral over the classical extremal surface. OK, and the point is you can now vary this thing with respect to rho 1 and get a quantum extremal surface formula from the Lagrangian corresponding to this plus the two area terms. OK, and here's where something kind of magical happens that we did not expect at all. So what happens is the quantum extremal surface formula takes this form. So this VGO is coming from varying the area terms, which I just erased. And this V entanglement entropy comes from varying that Rosenhaus-Smolkin formula that I wrote down. But the point is that this formula is a simple, inhomogeneous second-order ODE. And so it has a very simple solution that can be split up into a contribution from this and a contribution from this. So this is kind of the surprising thing. So this rho 1 is the first order quantum extremal surface piece. And this VGO is coming from varying those area terms, which I erased. So there was.
You just brought down the extremality for this.
That's right. This is just the extremality condition for that Lagrangian corresponding to, this is coming from Rosenhaus-Smolkin formula. This is coming from those two area terms, which I've erased. But x is the coordinate in Rindler. So rho is the radial coordinate, tau is the angular coordinate, and x is the coordinate that goes this way in Rindler. Exactly. Yeah. So we're at tau equals 0, and then there's some quantum surface described by this. So So here's what's kind of surprising is that it's like the entanglement entropy and the geometry are two independent forces that somehow pull on this surface independently. So you can sort of compute them individually and then just take their sum. Because the solution to this differential equation is just a sum of the solution where I only consider this potential and the solution where I only consider this potential because of the linearity of this ODE. So this is kind of the remarkable thing. And so what we computed is this, and we don't yet know how to fully compute this entanglement entropy term. But we can compute this and then compute the corresponding area terms. Okay, and what you get is this is the geometric contribution to the quantum extremal surface plus terms that depend on theta to the 4h and theta to the 8h. Okay, but the final point is that this is the punchline. When you include all these contributions coming from the area term, you find that it exactly matches the CFT answer. So you find that coming from the identity plus the stress tensor is exactly these two terms after all the dust settles. Okay, so that's the punchline, is that we find this agreement. So it seems like the area operator in the bulk, at least in this simple case where we have finite quantities, is encoded in the Virasoro identity block in the CFT, and we get an exact match between the two sets. Okay, so let me conclude, and there are lots of open questions. So we showed that this area operator is encoded in this identity block, and we initiated a program to try to link these quantum extremal surfaces, at least in this very special class of states, to the conformal bootstrap and the contributions from the CFT OPE data. So one thing we need to understand is we need to understand the Bulkentanglement entropy term. And I think conceptually we understand exactly where all the contributions are coming from. It's just a technically hard calculation. Okay. is it true in more general states? Can you construct such a dictionary? Maybe, as Raphael said, we're just in some very sweet spot where everything works out nicely. But maybe these divergences don't cancel for more general states, or certainly in higher dimensions, it's probably not as simple as this. So that's another question, is how does this work in higher dimensions? And in higher dimensions, you're going to have to start dealing with graviton entanglement. So here we ignored graviton entanglement. It was computed in a paper by Alex and Yorit and someone else who I'm forgetting. And they computed in graviton entanglement in this case, and it's just some topological term because gravity is topological in ADS3, and it basically just shifts the central charge. So it's not interesting. But in higher dimensions where gravity is dynamical, you'd have to start worrying about graviton entanglement. So how to compute this and how is it encoded in the CFT? And another interesting question, which we've been thinking about for a while, is how to understand stringy corrections to the quantum extremal surface formula. In the CFT, you can imagine including 1 over delta gap corrections to this 2 endpoint function that we computed, and asking what happens to the quantum extremal surface formula when you include these stringy corrections in the bulk. Okay. And with that, I'll stop and ask for questions.
It's a big program, so
Yeah.
how far are you along, and do you have any help, or is this just
It's mostly just me and Alex at this point. We're trying to recruit Eric Perlmutter to work with us on this, so he's been busy. But yeah, right now it's mostly just us trying to understand this step first. But yeah, there's a lot to do, certainly.
There's some good grad students here. You should talk to them.
Yeah, I would love that. That would be great.
So if no more questions, let's thank Tron again.